Okay, so in today's class, we will continue with from where we had stopped. Yes, in the previous class, we spoke about the probability distributions, the different kinds of. I introduced you all to the idea of random variables and what it means to have a probability distribution. And you all saw that there are two kinds of distributions that we can have. One is called as a discrete a distribution for a discrete random variable, and the other is a distribution for a continuous random variable. This is what we had talked about in the previous class. Okay, so we talked about random variables. What are the different types of random variables? We have discrete random variables and continuous random variables. Then we saw some example, of course, what a random variable really is. I told you the random variable is basically a function. Then what are the functions, the probability functions which are associated with this? So first we have the probability function, which is PF, and then we have the cumulative probability function, which is just the sum of the probability function. The cumulative probability function CPF, it always increases from 0 to 1, whereas the probability function, it can increase and it can decrease. Then we saw how the area under the probability distribution, in case of continuous distribution, it becomes PDF. In case of discrete distribution, we call it as PF. And the area under the PDF is, it gives you the probability that we're looking for. If let's say I want to find out what is the probability that a random variable lies within A and B, then all I need to do is find out the area under the curve between A and B. The probability density, the cumulative density function, which is CDF, that directly gives you that probability. All I need to do is just take the difference, and that is going to give you the same area. Then there are many different parameters of a distribution which we are interested in. One is known as the expectation value. Then another one is expectation value, by the way, is like the mean, okay, of any function. So if I find the expectation value of the random variable itself, that gives me the mean of the distribution. Then we talk about the mode. The mode is where the function, the PDF, takes the maximum value, that is the mode. Then we have the median. Median is where the CDF or the CPF takes the value half. Then related to the median, we have the lower quartile and the upper quartile. So lower quartile is where the CDF takes the value 0.25, and the upper quartile is where it takes the value 0.75. Then we have the variance. So variance, again, we can define it in terms, we can define it as an expectation value. So it's simply the expectation value of the square of the difference of the random variable with respect to its mean. Then finally we come to the standard deviation, which tells us how what is the spread of a distribution. So it is nothing but the square root, the positive square root of the variance. And we saw an example which involved rolling of a dice, of an unfair dice, where the probabilities of getting these different dot patterns were given, and we found out its mean and standard deviation. So this is what we had done in the previous class. So now what we're going to do is we are going to look at the discrete distributions first, and then continuous distribution. So to be more specific, the discrete distributions that we are going to talk about, we'll be mainly talking about two discrete distributions. One is the binomial distribution, and the other one is the Poisson distribution. Both are really important in understanding, doing your basic understanding basic statistical methods, often basic statistical processes. Both are really important. So these are the two kinds of distributions that we'll be talking about: the binomial distribution and the Poisson distribution. So binomial distribution, really easy to understand. You all are already familiar with the binomial distribution. So what is the binomial distribution? It is basically this. So suppose I have I can perform, let's say, some outcomes. Okay, outcomes. Now if you remember, I can perform some trials. Now you remember what is a trial? Trial is basically you run the experiment once. That is a trial. So a trial can have many different outcomes. Okay, the set of all outcomes is the sample space. So let us say I can perform identical trials, and these trials, there are two possible outcomes. Okay, so remember binomial, the word binomial, that means it's got to do with the number 2. Okay, that means there are two possible outcomes. So what is important here is there are two possible outcomes. One outcome, I call it as a success, and another outcome is, I call it as a failure. Okay, so success I refer to that event as A, and failure I refer to as B, or simply B will be A complement, because if it's not a success, it has to be a failure. Then let us say that the probability of getting a success is P. Okay, then the probability of getting a failure will be simply 1 minus P, and that probability of getting a failure I call it as Q. Okay, why will it be 1 minus P? Because there are only two possible outcomes. So the probability of the first outcome plus the probability of the second outcome will give us the total probability, and that total probability has to be equal to 1. So that means P plus Q must be equal to 1. So therefore, if I just know P, I can find out what is Q. So if P is equal to 0.25, then Q will be 0.75, and so on. Okay, so that basically is the definition of that becomes an ideal situation where you can use the binomial distribution. So any distribution where something like this happens, that's a binomial distribution. So now that is the definition part. Now let's try to understand this using some examples. So there are a couple of examples, some very familiar examples. Let's take the first familiar example of the tossing of a coin. So let us say I define, so here you have to remember the way you define success or failure is totally up to you. How you want to define success and how you want to define failure. Okay, so here the word success or failure has got nothing to do with the positive and negative connotations. In our or everyday conversation we talk about success and failure. That has got a different meaning. Okay, I'm not talking about that meaning at all. Okay, so here it's totally up to you how you want to define your success or your failure. So let us say while tossing of a coin, let us define success as landing a tail. So if you get a tail, that is success for you. Okay, so before a cricket match, there is they have the tossing of the coin to decide who is going to decide the batting sequence, like who's going to start their own innings, right? So there are two captains who are facing each other and they want to toss the coin. So let us say the ex-captain of Indian team, Virat Kohli, he says heads. Okay, so for Virat Kohli, he has defined success as head. So that means for Virat Kohli's success, so failure will be getting a tails. Okay, so and vice versa. If instead of saying heads, if he says tail, then tail will be the success. Getting a tail will be the definition of the success. Then in that case, getting a head will be a definition of failure. So as we all know, for tossing of a coin, there are two sides of a coin. There cannot be more than two sides. So the probability is 50-50. When you toss a coin, you'll get probability 50-50. So the probability of success is 0.5, which means the probability of failure is also 0.5. So 1 minus P. So this is an example of a binomial distribution, such a tossing of a coin where you have these two outcomes. Now, can you get can you get a binomial distribution using a rolling of a dice? You know that rolling of a dice, if you remember, there are 6 possible outcomes. So if there are 6 possible outcomes, then can we define success and failure? Because when I say success and failure, when I talk about a binomial distribution, we are talking about only 2 possible outcomes. But whereas in the case of rolling of a dice, there are 6 possible outcomes. So how can we define success and failure in this case? So now remember, the outcome can be many, but the way you define your event, the success or failure, it's totally up to you. So let us say, in case of rolling of a dice, let's say I define success as obtaining a number greater than or equal to 5. Okay, so this could be a scenario. Let's say you are rolling a dice in a game of Ludo. Okay, so in a game of Ludo, you want to get a number as high as possible. Okay, so the most favored number that you want to get in a game of Ludo will be 5 or 6, right? So you define success. If you get 5 or 6, that is success for you. Anything less than 5, that is failure for you. So you define, in case of rolling of a dice, you define your success as obtaining a number which is greater than or equal to 5. Okay, so that's how you define success as. Just one moment. Okay. So if I define success as obtaining a number greater than 5, then what will be the probability of success? Probability of success will be simply because I want a number greater than or equal to 5. So there are only 2 possible outcomes which satisfy this condition. One possibility is getting a 5 itself, and the other possibility under the outcome is getting a 6. So either if you get 5 or 6, either of these two will constitute a success. So the probability of getting a 5 plus the probability of getting a 6, that total probability, sum of these two will give us the probability of success. So probability of getting a 5 is 1 by 6. Probability of getting a 6 is also 1 by 6. So the sum of these two, getting 1 by 6 or 1 by 6, 1 by 6 plus 1 by 6, it gives you 2 by 6, which is 1 by 3. So in this case, I have defined my success in this way. So the probability of success is 1 by 3. If the probability of success is 1 by 3, then the probability of failure is obviously obtaining a number which is lesser than 5. So that is going to be 1 minus 1 by 3, and that is going to be 2 by 3. So these are some examples where you can actually apply the binomial distribution. Is this clear to everyone? Some examples of applying where the binomial distribution is applicable. Is this clear, everyone? Any questions? Okay, so I've done no questions, then we'll proceed. So now let us go ahead and we define a random variable. Okay, so I have a binomial distribution. So what about the random variable? Okay, so let us say I have a binomial random variable. Okay, this binomial random variable, I call it as, a binomial random variable. I call this random variable as x. So how do you define this x? We define this x as the number of successes that you get in n trials. So if I have n number of trials, like for instance, in case of tossing of a coin, okay, so you define success as landing a tail. Okay, so let's say you toss the coin many number of times. Okay, so let's say you toss the coin 100 times. Okay, and you get tail, let's say 30 times. Okay, so in that case x will be 30, because x is number of successes in n trials. So in 100 trials you have got 30 times you have got tails. So in that case the value that the random variable is going to take 30, or any other value. Okay, now all these trials have to be independent. This is another important point that you need to keep in mind regarding the binomial distribution. All the trials have to be independent of each other. So if I toss a coin now and I toss a coin after like 1 second, or after 1 year, or after 1 week, okay, these coin tosses will always be independent of each other. So all the trials are independent. So that's an important criterion for any random variable, any process to be having a binomial distribution. So out of n trials there are x successes. Okay, we have x times that we have got success, and the probability with which we have got success is p, and that means there are n minus x failures. So one such event if I take, okay, so if I just if I take toss 100 coins, okay, toss the same coin 100 times, or toss 100 coins, both of them are exactly equivalent. So let's say there are 30 times there we have got success. Then there will be 100 minus 30, that means 70 times that we have got failure with this probability. Then one such event will be this, running it 100 times. So once the probability of a single event will be, because I have got success 30 times, so I have got success 30 times, so the probability of success, which is 1 by 2, half, we have to raise it to the power of 30. Okay, and the probability of failure is also half, we have to raise that to the power of 70. Why? Because first time you get a success, next time you get another success. So these two, because you got the first success, now you want to see what is the next success. So you have to keep on multiplying these probabilities. You have to multiply one after the other, because I'm taking n trials as one single group. Okay, then there are also, how many such events can we have? We can have that means, in other words, how many combinations can I take out of n such trials? What are the different ways by which I can get x successes? So if you want to understand this, what are the combinations of x identical objects out of n? This is what I'm talking about. So let us say I want to toss the coin, let's say 10 times, okay, or let's say 5 times. I want to toss the coin. Okay, so let's say I want to toss the coin 5 times. Okay, I want to know what is the probability. Okay, I want to know how many times do I get, let's say, success, 3 successes out of 5. I want to know that. Okay, so probability of success is half. Okay, so now what are the different ways by which I can get that? Okay, let's try to figure this out. So you toss the coin once, let's say you get a tail, right? then next time you toss it, you get head. So now remember, this is a success, okay? And next time again when you toss this, you again get head, and the last two time obviously you must get tail, because we want to get it three times. We want to three successes. So first we have a success, then we have a failure, then another failure, then another success, another success. So this is one such possibility, okay? Is there any other possibility by which I can get 3 successes out of 5 trials? Yes, there are, right? There are other possibilities also. Another possibility could be you could get a head now, then followed by 3 successive tails and then another head. This is another possibility. You see? So how many are different ways are there in which I can combine these different x objects out of n? How many ways are there? There are ncx ways by which I can do that. And what is ncx? You know, this is combination, right? So ncx is simply n factorial divided by x factorial into n minus x factorial. Okay, so there are these many number of ways by which I can get, you know, what I'm looking for. So what is the total probability that I get x successes out of n trials? So I have to consider the probability, that is, let's say this is probability 1, this is probability 2, and so on. Okay, all of these individual probabilities, I just need to add all of these individual probabilities. Okay, and that is going to give me the total probability. Okay, so instead of adding all of them, what I do is, because each of these cases, the probability, each of these events, okay, the probability of this event is p to the power x q to the power n minus x. The probability of this event is also p to the power x q to the power n minus x. So if I add them, all I need to do is find out how many such events are there, multiply that number of events with the probability of each event. And the number of such events is ncx. So all I need to do is, I just need to multiply ncx, the number of events, okay, with the probability of each event. And the moment I do that, this is equation number, I call it as equation number 1. This gives me the probability function of the binomial distribution. So the probability function of a binomial distribution is this. It is simply ncx into p to the power x into 1 minus p to the power n minus x. Or you can write this as ncx. By the way, some books they write it also like this. This ncx is also written in this way in some books. They write it as bracket nx. This is another notation for this ncx. So this is simply equal to ncx p to the power x, and 1 minus p is q to the power n minus x. So this is another way to write down the same probability function, the pf of the binomial distribution. Is this clear, everyone? All of you understood? If it's clear, then I can proceed. Otherwise, the next few topics will not make any sense. Can I proceed, everyone?
Yes, sir.
Okay. Then we come to the concept of the binomial variate. Okay, so now we are going to use some, I'm going to introduce you all to some notations. Okay, so if I have a random variable x, and we know that this random variable x, it follows a binomial distribution. That is, if I have n trials, okay, and the probability of success is p. Okay, then, and we know that this x, the random variable x, it follows a binomial distribution. Then in that case, we call this random variable, it's given a special name, we call it as a binomial variate. Okay, so moment I say binomial variate, so what does it mean? What is the meaning of this phrase? Meaning of this phrase binomial variate, what it means is a random variable with a random variable with a binomial distribution. Okay, so a random variable which has got a binomial distribution, that is what is called as a binomial variate. That's all. Okay, nothing more than that. Okay, so that's what you need to remember. So we write it in this way. We write it in a shortcut. Instead of saying suppose I have, instead of saying let's say you want to write, okay, you want to write this, x is a random variable with binomial distribution. Okay, you want to describe a random variable. This is another way to, this is one way to describe it. Another way to describe it is, we could say X is a binomial variate. Okay, this is another way to describe this. Or just as a shortcut, you could just say X similar to, okay, this is this similar is called similar to bin for binomial, and inside this you put the parameters of the binomial. And you know, for binomial there are two things which are important. One is the number of trials, and another window is the probability of success. These are the parameters. N and P are the parameters. So writing like this, or writing like this, or writing like this, it means the same thing. So if I write something like this, it means X is a binomial. X is a binomial variate with number of trials N and probability of success P. That's what this means. Okay. Now coming back, what is the mean and variance of a binomial variate? Okay. If, again remember, I said like this, okay, X, this means X is a binomial variate. If I say X similar bin N comma P, it means X is a binomial variate. So if X is a binomial variate, then the mean of the distribution is simply N into P. That's all. Okay. N is given, P is given, so mean of the distribution is N times P. What about the variance of the distribution? The variance of the distribution is simply NPQ. Okay, so it is simply N into P into 1 minus P, and you know 1 minus P is equal to Q. So the variance of such a distribution is NPQ. So these are the two important things that we need to keep in mind. A binomial variate with N is the number of trials, P is the probability of success for any one outcome. Okay, and if X is a binomial variate, then the mean of the distribution will be NP and the variance of the distribution is NPQ. Okay, I'll not prove these two results, because the proof of these two results you will encounter in your third semester when you do the course on research methodology. So there's a small module on probability and statistics. Again, here in this course, we are going to only talk about a little bit of probability distributions, that's all, and we are not going to talk much about statistics. In your research methodology, you will discuss statistics in far greater detail. So over there, we will prove these two results. All right. So that's the mean and the variance of a binomial variate. Okay. So you can, I can plot this to you. Okay. You can see how the plot of a binomial variate looks like. Okay, so these are three plots. The first plot, okay, here N is 10. I'm taking 10 trials, P is equal to 0.5. The probability of success is 0.5. Okay, so this is how the for let's say a coin toss, I want to toss the coin. How do you read this? How do you understand such a graph? Let me take this to my slide. Okay, so here we have, how do you understand this? So this is so X is a binomial variate. We write it like this, and we write it as N comma P. What is N? N is 10. So there are 10 trials, and what is the probability of success? The probability of success is 0.5. Okay, so this is the distribution of a binomial variate, which looks like this. Now, how do you understand this? Now remember, this is X. Okay, so how do you define success? Remember, the success, the way we have defined in a binomial distribution, we define success as number of successes, or rather not success, we define X in this way. So X is the number of success in N trials. Okay, in N trials. So this an example of such a distribution, you will get, let's say, tossing of the coin. Tossing of a coin. Okay, how do you know this is tossing of a coin? Because you can see the probability of success. The probability of success is 0.5, because it's 0.5 coin toss, it gives you that kind of a probability. But then did we not expect 50-50, right? We would have expected 50% to be success, 50% to be failure. But why are we getting something like this? This is where you have to understand what is happening here. What is the meaning? If I say something is 4, okay, what does this mean? Can anyone tell me? What does this mean? What does this mean? It means 4 tails. 4 tails during 10 tosses. Is this clear, everyone? When I say when x is 4, it means what is the probability of getting 4? So if you toss the coin 10 times, what is the probability of getting 4 tails? Okay, and that probability turns out to be around 0.2. Is this clear, everyone? This is the meaning of each of these bars that I have over here. Okay, so what is the most probable result that you expect when you toss a coin 10 times? What is the most probable result? Can anyone tell me? Tossing of a coin. When I say 50-50 chance, when you toss a coin, 50-50 chance, what is the most probable result? Or rather, I should say, what is the most probable event? Can anyone tell me? When you toss a coin 10 times, most probably what will happen? We say 50-50, right? So if you toss a coin 10 times, most probably what you will get is, you will get 5 tails, right? Agree, everyone? During Is this clear or not? 5 tails during 10 tosses. Correct, everyone?
Yes, sir.
Okay, so if it's 5 tails during 10 tosses, where is 5 here? 5 is here, right? Can you see? If this is 4, this is 6, then this must be 5, right? What is the probability? So what does this mean? When I say 5, what does this mean? It means this. 5 tails during 10 tosses. And what is the probability? That has got the maximum possible probability, right? The probability that you will get 5 tails during 10 tosses, that probability has got that event has got the maximum probability. Other events, they have got lesser probability. So if I say something like this, what does this mean? It means what is the probability of getting 1 tail out of 10 tosses? That probability is very small. What is the probability of getting 9 tails out of 10 tosses? 9 tails out of 10 tosses means 1 head out of 10 tosses. Because heads and tails, they have similar probability. This probability of getting 1 tail out of 10 tosses or 9 tails out of 10 tosses, these two probabilities will be identical. Does it make sense now? Is this clear? This means 1 tail, 9 heads. This means 9 tails, 1 head. They are identical. This means 2 tails, 8 heads. This means 8 tails, 2 heads, because I have defined probability as success as getting a tail. Does this make sense, everyone? So the most probable result is you will get 5 heads and 5 tails. So this means 5 tails and 5 heads. This is what it means. Clear, everyone? Understood?
Yes, sir.
Okay, so this is how the distribution will look like, and this is what is being shown over here. So what I have done is I have drawn 3 graphs. Okay, there's 3 graphs. I have kept the probability of success to be the same. Okay, now one more thing you see, what is the average value? Where is the average value? Average value is, you can make sense, you can easily see average value is, right, what do you do? 1 into this value plus 2 into this value plus 3 into this value plus 4 into this value. You will get average somewhere in the center, right? And that's exactly what has happened here. This average is at the center. So out of 10, because the probability of success is 0.5, if you toss the coin 10 times, Okay, the mean is somewhere going to be the average value, the average number of tails that you are going to get. That average number of tails will be 5, and that's why you can see it reaches a maximum value somewhere at 5. But what if I increase the number of trials? Okay, let's say I increase the number of trials to 50. Then where do you expect, this is what happens, where do you expect the mean to be? In case I make the number of trials, I make it 50, the probability of success is still 0.5, but the number of trials is 50. In this case, how many what is the average number of tails that you will get out of 50? Average number, what do you expect? Anyone? What is the mean value of this distribution? Here the mean value is here, right? This is the mean value, correct? The average value, the average number of tails that you will get is 5 out of 10, right? Halfway, because the probability is 0.5. So if you have 50 trials, then what will be and the probability of success is 0.5 again, then where will the average be? Can anyone tell me? Anybody? Study this and tell me what will happen here. Vishal, what do you think? The average value. Riba? Anyone? Laboni is there? Goody, where do you think the average value will be? Am I still audible, by the way?
Yes, sir.
Okay, just tell me, where do you think will the average be if I take n equal to 50? Total 50 trials. 10 trials, I got the average to be 5, right? 5 here. This was the average. If I take 50 trials, then 50 tossing of coin, then where will I get the average to be?
25. Will it be 25?
Yes, it is 25. See, it is 25. It has to be, right? Makes sense, no? Because if I toss the coin 10 times, on an average you'll get 5 tails, 5 heads. That's the meaning of that 50-50. Okay? If I toss the coin 50 times, on an average you'll get 25 heads and 25 tails. This is what it is telling exactly that. You get at 25 is the average value. I'm defined success as number of tails. So you will get 25 tails. Okay? Because the average is 25. If I make it 100, then what will happen?
50.
It will be at 50. The average value will be 50. Is this clear, everyone?
Yes, sir.
Okay. Now, even though it looks like, the graph, if these three graphs, if you look at them one after the other, it looks like as if as you are increasing the value of n is 10 here, it has become 50, it has become 100 here. It seems like as if the graph is becoming narrower and narrower, right? That's what it looks like, right? That's what it seems to be here, correct? But that is actually not the case, okay? Because the variance is npq. Remember, variance is npq. Okay, so we can calculate the variance. Why it is appearing it to be like that is because here I have plotted the graph from 0 to 10. Here I have plotted from 0 to 50. Here I have plotted from 0 to 100. So if you want to get a better picture of what's happening here, I should make the x and the y limits. And also one more thing, you see the maximum probability here, I'm plotting 0.25. Here it is in the range of 0.1. Here it is 0.08. You can see the probabilities are actually decreasing, even though it looks like the probability values are remaining more or less the same. So you will be able to understand it far better if I make the x and the y axis, if I make them the same, then you'll understand it better. Let me do that. You see what's happening here? This is for n equal to 10. Okay, now you see I'm plotting from 0 to 100. Okay, I'm plotting from 0 to 100. So n equal to 10, you see we're having a very high probability of getting these numbers from 0 to 10. Now I make n equal to 50. You can see the mean has now shifted. Here the mean was here. Now the mean has shifted to 25. You can see here the mean has now shifted to 25. 25 is somewhere over here. But when the mean has shifted, when you increase the number of trials, the mean has shifted towards the right side, but at the same time, the height of the distribution has also decreased. Correct? And when I make it n equal to 100, you see, again it shifts towards 50, and you see the height has decreased even further. Do you expect this behavior? Do you expect the height to decrease? Should the height really decrease with increasing n? What do you think? Should the height decrease or should the height remain the same? Anyone? It should decrease. Okay, it should decrease. Why should it decrease? Because the variance, because as n increases, because p and q is remaining the same, p and q are same, n is increasing. As n increases, the variance increases. And you already know, in the previous class we talked about what does the variance tell us. Variance gives you standard deviation, and standard deviation tells you what is the spread of the distribution. More the variance, more the distribution is spread around. So here this is going to be narrower because here n is 10, so the variance is small. That means the spread of the distribution will be less. Here n has increased, so the spreading will be more. Here the n has increased even more, it is going to spread even more. Okay, so because the distribution has spread, but the total area has to be same, right? The total area under the distribution always has to be same. Do you agree? The total area under the distribution, that is these blue rectangles. If I add the area of all of these blue rectangles, the total area must be same in all the three cases. Do you agree or disagree? Yes or no? Anyone? The area under the distribution, should it decrease or should it remain the same? Anyone? Vishal, you have been silent. Laboni, what do you think? Should the area remain the same or should it decrease? As it is it of course it should decrease, but why should it decrease? That's the question. Laboni? Yes? I'm just interested in knowing your idea. What do you think? What could be the reason? Goody? Anyone? Yes?
Sir, no clue.
No clue. You see, what should be the total? What should be the total area under the probability function? What does the area under probability function give us, Lavani? The sum of all probabilities, right? What should be the sum of all probabilities? What should be the sum? No, sum, the total probability of first event plus probability of first outcome plus probability of second outcome plus probability of third outcome, or rather I should say probability of first event plus probability of second event plus probability of third event, and so on. Sum of all of these must be equal to 1, no? Because any one of these events can occur. Like for instance here, if I toss a coin 10 times, any one of these possibilities can happen. Either you may get only one tail in one scenario, you may get in another scenario you may get two tails, in another case you may get three tails, four tails, five tails, and so on. So if I add all of these probabilities, that will give me the total probability. One of these events should occur, no? So what is the total probability? Total probability is the sum of all probabilities, which must be equal to 1. Probability cannot be greater than 1, so it has to be equal to 1, right? Make sense?
Yes, sir.
Okay, so if the total probability has to be equal to 1 and the area under the PF gives you the total probability, so what is the total area that we are seeing in this graph? The total area is 1, right? What is the total area that we are seeing in this graph? Also 1, right? What is the total area that we are seeing here? Also 1. But what is happening is the height is decreasing. If the height is decreasing, that means it has to get wider. Sorry, the graph is getting wider. If the graph is getting wider, but if the height remains the same, then in this case and this case, we will get larger, the probabilities which are areas which are greater than 1. That is not possible. So that's why if the width of the graph, if the width of the distribution increases, then the height of the distribution has to decrease. So that's why it is not at all surprising that the height is decreasing. Make sense, everyone? Is this understood?
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
Great. So now we have something called as a binomial recurrence formula. The binomial recurrence formula is simply, it tells us that if you know the probability, this is one of the really cool features of binomial distribution. That is, if you know the probability at some value of x, you don't have to apply the same formula again and again. Okay, this formula for finding the binomial distribution, this one, ncx p to the power x 1 minus p to the power n minus x. You don't have to keep on repeating this formula again and again. If you know the value of the distribution at 1x, okay, at any 1x, then you can find out what is the value at x plus 1. So for instance, if I know what is the probability, at x equals 1, I can find out the probability at x equals 2. And knowing the value of the probability at x equals 2, I can find out the probability at x equals 3. And knowing this, I can find out what is the probability at x equals 4. So this is known as the recurrence formula, and it is like this. So probability at x plus 1 is equal to p by q times n minus x by x plus 1 times the probability at x equals to x. Okay, so that's the recurrence formula. By the way, I just written a little Python code which shows that you will get the same thing if you use a recurrence formula. I know that many of you are not at all used to programming of any kind. Like, there are many students who have not had any exposure to programming in their life, I'm sure, but don't worry about this. Don't worry about the code here, because when you go to your third semester, you will learn programming. Okay, you will learn 2 programming languages. You'll learn Python and you'll learn C programming language. So don't worry about it. There will be a time, like after one more semester, you will be able to start making plots like this on your own. Okay, so that's why I'm hiding these code right now. What is important is the plot. So you can see here, this is again a binomial distribution, but I have obtained this distribution not using this formula. Here I obtained these distributions using the formula. Okay, but here in this plot I have obtained this not using the formula, but using the recurrence formula. Okay, using this formula. Okay, then there are certain theorems of binomial distributions which makes our job easy. The first theorem is this theorem. That theorem is called as the sum of binomial distribution. So what it says is, if I have independent binomial variates whose number of trials are different, but the probability of success is the same, then the sum of all of these binomial variates is also a binomial variate. Okay, to be specific, let's say I have 2 independent random variables x and y. And these random variables x and y, they are also binomial variates, as you can see here. Okay, this means x is a binomial variate. The number of trials for x is n1 and y is also a binomial variate with number of trials n2. Now let's say I have another random variable z, and this z is simply the sum of these 2 binomial variates. Okay, then this theorem says that z is also going to be a binomial distribution. So it becomes actually very easy. All you need to do is just take the 2 binomial variates and just add the number of trials. That will give us the mean, using that n1 plus n2 times p, that is going to give us the mean of this new distribution. Okay, so the sum of 2, this is what you need to remember, the sum of 2 binomial variates having different number of trials but the same success probability, it is also a binomial variate. Okay, so this is what you need to keep in mind. Here I have said about only 2 independent binomial variates, but you can extend this idea forward to the case where I have n number of such binomial variates. So if I have, let's say, capital N number of such binomial variates, okay, these are xi, then Z is simply the sum of each of the all of these binomial variates, then Z will also be a binomial variate. So here number of trials for Z will be the sum of the individual number of trials, and the probability, I'm assuming that all of them have the same probability P. Okay, so this is a general form of this theorem. Now don't worry about how to prove this theorem. This theorem we will prove it, like I said, in your course on research methodology in your third semester. So when we go there, I'll use the concept of there's something called as moment generating functions. So we will use that concept to prove these really interesting results and very important results. Okay, so this brings me to the end of binomial distributions. Now I'll move on to Poisson distribution. So before I move on to Poisson distribution, does anybody have any questions or any queries? Any concerns? Okay, I'll take it as if you don't have any queries at present. All right. Now let's move on to Poisson distribution. The Poisson distribution is a very interesting distribution. Okay, because it is a distribution which you'll see. Yeah. Pardon?
Will you please
Zoom in where? Which part?
I can't see the writing.
Okay, but I think you can, because if I zoom in even more, then that is going to spoil. This is the maximum zoom that I'm able to go. Because if I zoom in a little bit more, then what happens is it spoils the formulas which are appearing on the screen. One thing which I can suggest is you can pinch and zoom on your screen. My presentation. Can you try that? On your screen, just try to pinch and zoom my presentation. Is it increasing in size?
Let me check.
Yeah, just try it out.
Yes, sir.
Okay, right. So coming to the Poisson distribution, a very important distribution, because in many natural systems we find the Poisson distribution. Okay, so one thing that you need to keep in mind is it is very similar to a binomial distribution. In fact, Poisson distribution is a binomial distribution. Okay, that is the binomial distribution in certain limits. And what is the limit? The limit that the number of trials goes towards infinity, and the probability of success, it tends towards 0. As you can see over here in this example, you saw the number of trials, as it was increasing, this entire distribution was moving towards the right side. And also what was happening is the distribution was getting wider and wider. As the distribution is getting wider and wider, the height is decreasing. That means the P is decreasing. Okay, the probability of success, it was becoming smaller and smaller. Okay, the probability of getting a success, because we are increasing the number of trials. Okay, so we have to increase n and decrease p in such a way that even though n is increasing and p is decreasing, the product np, it remains constant. Okay, I'll give some physical examples of where you can expect this. But the fact is, just because n is becoming infinity and p is becoming 0 does not mean that the average of the distribution will become 0 or infinity. No, because average for a binomial distribution, average is np, as we have already seen. That average should remain the constant. Increase in n is offset by the decrease in p. As a result, keeping the np, the product np, to be always constant. Okay, so when that happens, then the binomial distribution, we no longer call it binomial distribution, we call it as the Poisson distribution. Okay, so where do we need the Poisson distribution? In case of binomial distribution, you have seen here, in case of binomial distribution, here the number of trials was known. The number of trials was known. It was n. We already knew the number of trials. But in case of, there are many scenarios where you don't know the number of trials. The number of trials are not known. Just some average value is known. Some average rate is known. That becomes a good place where you can go ahead and apply the Poisson distribution. Okay, so Poisson distribution, but you need to keep in mind are these 3 points. It is like a binomial distribution in the limit dash n tends to infinity and p tends to 0, keeping the product np equal to lambda being a constant. And we can use the Poisson distribution wherever the number of trials is unknown to us. Then we can use a Poisson distribution. Okay, so now let's look at random variables which follow a Poisson distribution. So the Poisson distribution it expresses the probability of a given number of events occurring in a fixed interval of time and space. This is important, okay? A Poisson distribution, it gives the probability of a given number of events which occur in a fixed interval of time or space. Okay, and if these events occur with a constant mean rate and independent of the time of the last event. Now, I know this is a lot of things to swallow, but right now I'll not go, I'll explain this further. We'll be doing an example, okay, and in this example you will see how this works. So right now just focus on the maths part of this one. So suppose I have a discrete random variable x, then this discrete random variable x is said to have a Poisson distribution with a parameter lambda, and this lambda is always positive if it has got a probability function which is given as lambda to the power x minus e to the power minus lambda to the power x times e to the power minus lambda by x factorial. So if it follows a probability function like this, then this is a Poisson distribution. Okay, and again I'll explain this a little bit later. This sentence I'll explain it when we do the example. Next, what is a Poisson variate? So just like how we had talked about the binomial variate, we called a random variable which follows a binomial distribution, we call it as a binomial variate. In a similar way, we could talk about a Poisson variate. What's a Poisson variate? A random variable which follows a Poisson distribution. Okay, and the mean or the rate of occurrence, this lambda you can understand it as the mean of the distribution or the rate of occurrence. Okay, that is called as the lambda. Then we call x as a Poisson variate and we write it in this way. For binomial it was so for binomial we had this, for binomial variates x is said to be a binomial variate if we write it as bin, and inside the bracket we put the parameters. The parameters are number of trials and the probability of success. What about Poisson? Okay, so a random variable x, it is said to be a Poisson distributor. So instead of bin we write it as PO. Okay, and inside the bracket here these are the parameters. Here the parameters, because we don't know what is n, because like I said, a Poisson distribution is applicable when you don't know the number of trials. So we don't know the number of trials, we don't know the probability of success also. All that we know is the mean rate of occurrence. So there's only one parameter. So binomial distribution is it takes two parameters. Poisson distribution, it only takes one parameter, which is lambda, and we write it in this way. Okay, so lambda is a single parameter which controls a Poisson distribution. Okay, so now coming to the example that I was talking about. Okay, now listen carefully. Okay, this is where I'm going to explain this line. Okay, a Poisson distribution expresses the probability of a given number of events occurring in a fixed interval of time or space. So remember, whenever you are having a fixed interval of time or space, okay, so that means we are talking about a Poisson distribution. An example, let us say there is on a highway there is a toll plaza. Okay, there's a toll plaza on a highway, and let's say you are curious and then you just start counting the number of vehicles that cross the toll plaza. So what you do is, every time a vehicle crosses, or maybe you don't want to do it by sitting there at a toll plaza, let's say you put some device. That device, it will register a count the moment a vehicle crosses a toll plaza. Okay, so you count how many vehicles have passed by. Okay, how many vehicles have passed by this toll plaza, and you find out in 24 hours. Okay, so you in 24 hours, let's say you count certain number of vehicles which have passed by. Okay, so you do that for, let's say, 5 days. Okay, so let us take a scenario. Let me take the example here. So let's say this is the toll plaza, this is the toll booth. Okay, and there are cars which are crossing. This is the toll booth, and let's say there is a car which crosses this toll booth. Okay, this is a car which crosses the toll booth. Every time the car crosses the toll booth, there is a counter which is keeping a count of how many cars are passing by. So let us say after 5 days. After 5 days, you have counted 636. After 5 days, you have counted that 636 cars have passed by. Okay, 636 cars in 5 days. So this implies how many cars in 24 hours? All you have to do is 636, because 24 hours is 1 day. So there are 5 days, so you divide by 5. So that gives us 127.2 cars. So in 1 hour, how many cars? 1 hour. So you have to divide by 24 hours. Okay, so that gives us 5.3 cars in 24 hours. So remember, when I say 5.3 cars, it does not mean that 5 cars and 30% of the sixth car have passed by. It does not mean that. Okay, it is just an average value that you are calculating. Okay, what you are calculating is an integer only. You have calculated 636. This is an integer, but that is over 5 days. So when you divide, after division over 1 hour, you will find it to be 5.3 cars. So this does not mean that a fraction, 5.3 fraction, 5 cars and 30% of the 6 car, it does not mean that. Okay, it is just an average value that we have here. So we have let's say you have observed that 5.3 vehicles cross a toll plaza per hour. Okay, then we want to know, okay, let's say X is the number of vehicles crossing during a particular hour. Okay, so now what you have done here is, you have given the total count over 5 days. But does it mean that at all times, at all hours of the day, same number of cars will pass? Does it happen? Will exactly 5.3 cars, exactly 5 cars, will they always pass? Let's say if I were to plot this during the entire day. Okay, let's say this is time during the day. Let us say this is 7 a.m. to 8 a.m. Then this is 8 to 9, this 9 to 10, 10 to 11, 11 to 12, 12 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on. So how will it look like? How will it look like? Will it always be constant? Of course not. 7 to 8, we will have a small number of vehicles which will pass by. 8 to 9, the number of vehicles will increase. 9 to 10, that's like rush hour, no, everybody is going to office, so the number of vehicles passing through that will increase even more. Then 10 to 11, it will decrease. 11 to 12, it will decrease. 12 to 1, very few vehicles. 1 to 2, again very few vehicles. 2 to 3, maybe no vehicles at all. 3 to 4, again we'll have some vehicles. 4 to 5, people are returning from the office. Like 5 to 6, we'll have some more rush hour, something like this. So this is on an average, this is what you will be observing. Okay, so where is this 5.3? 5.3 is somewhere over here. 5.3 is the average value. So this is your 5.3. Okay, so now let us say I want to find out during a particular hour. Okay, I want to find out during a particular hour how many cars have passed by. Okay, I want to find out the number of vehicles which have passed during a particular hour. So this is what I want to find out. So this is a Poisson variate. The number of vehicles which pass by during a particular hour, that is a Poisson variate. And we write this as, because the lambda, what is lambda? That is the average value. That's the average number of cars crossing per hour. So that becomes your parameter for the Poisson distribution. So it will follow a Poisson distribution of 5.3. So X is a Poisson variate with parameter 5.3. Is this clear? Is this clear to everyone?
Yes, sir.
Okay, so another example is this from, let's say, astronomy. Let us say I have a satellite which is in space, and this satellite is detecting photons. So you could have a scenario like this. So I have, this is the Earth, okay, and there is a space satellite. So basically, what is a satellite? Satellite is space observatory. Is basically, it's a telescope, okay, and those wings that you see, these wings contain solar panels. Okay, so we have solar panels on either side. These are just to power the satellite. So basically, this is a telescope, and there is a detector, and this detector, let's say, detects X-ray photons. So from some distant star, there is some star which is far, far away. Okay, there's some star far, far away. From this star, let's say there are some. It is emitting photons. Okay, so let's say there are X-ray photons which are coming towards the Earth. It's coming in all. It's going in all directions, of course. It's emitting X-ray photons in all directions. We are only interested in the X-ray photons which are arriving towards the earth. And so to catch these X-ray photons, we have put a telescope. So what this telescope is going to do is, it has got a detector. This detector is going to detect the number of photons. So every time a photon hits, it will count, just like you did over here. Every time a car crossed the toll plaza, you kept a count of the number of cars. So every time a photon hits the detector, it kept a count of the number of photons. Okay, so let us say I have a satellite, and this satellite, it detects 0.00024 photons per second. Does it mean that it detects a fraction of a photon? Obviously not, because you cannot fragment the photons. It is just an average number. Okay, over a long period of time, let's say over 5-6 hours, it is detecting one photon, right? Then you divide it, or let's say over 20-30 minutes, it is detecting, let's say, one photon. You are dividing that one photon over these the total number of seconds. So that's why we are seeing this value here. Again, the same reason as for the car. So this is the average value. This is the average number of X-ray photons which are detected per second on the satellite. Then I can talk about a random variable, which is basically the photon count rate. Okay, what is the rate at which photons are being detected? So what is rate? Rate is per unit time. So count rate means the number of photons per unit time. So x is the photon count rate. So this becomes a Poisson variate, and we can write this x as a Poisson variate with parameter 0.00024. Okay, so these are two examples of Poisson variate, and as you can see here, these are very, very useful in our practical experience. Okay, so that's a Poisson variate. Is this clear, everyone? Understood? Okay. Next, what is the mean and variance of a Poisson variate? Very easy. The mean and variance, they are exactly the same. Lambda is the mean, lambda is also the variance. Okay, a Poisson distribution is the only distribution where the mean and the variance are going to be always the same. If the mean is lambda, the variance is also lambda. Okay, so that's a mean and variance of a Poisson variate. Okay, so I have a plot here. Oops, just a minute. I've missed out something, just give me a moment. I might have deleted some values here. Let me just try something. Okay. Right. Okay, so we have, this is a Poisson distribution, and as you can see here, for three values of lambda, lambda equal to 1, lambda equal to 5, and lambda equal to 10, this is how the distribution varies. For lambda equal to 1, this is how it varies. For lambda equals 5, okay, you can see the mean now moves towards 5. So 5, this is 5 here, this is the mean. Lambda equals 10, this is the mean, and so on. And as you can see, as the mean increases, it spreads out more. Why? Because the variance is directly proportional to lambda. So as lambda increases, variance also increases. Variance increase means the deviation from the mean also increases. So that's why the plot becomes broader and broader. Okay, so that's your mean and variance of a Poisson distribution. Okay. Then like your binomial distribution, Poisson distribution also has got a recurrence formula. So if you know the probability at x, you can find out the probability at x plus 1 using this recurrence formula. Now an interesting result, that is the Poisson distribution. Like I said, the Poisson distribution is similar to a binomial distribution, and it is basically the limit of the binomial distribution. So there is a little proof of that same thing. So Poisson distribution is a limit of the binomial distribution. So let us say I have n number of intervals, and p is the probability of success in any one of these intervals. Then np is equal to lambda. Let's say lambda is fixed. Okay, then the probability of x successes and n trials, I'm just taking this result from the binomial distribution, because in the binomial distribution this is what happens. In binomial distributions we have ncx p to the power x 1 minus p to the power n minus x. So I'm just taking this result, borrowing this result from binomial distribution and just using it over here. So for binomial distribution, ncx p to the power x 1 minus p to the power n minus x. So now this ncx I expand it. It is simply n factorial by x factorial into n minus x factorial. So here we're going to use a couple of results. The result is this ratio n factorial by n minus x factorial. If I take the limit as n tends towards infinity, this is approximately equal to n to the power x. And another limit is 1 minus p to the power n minus x. Here there are the quantities p and n. If I take the limit of this quantity 1 minus p to the power n minus x, where n goes to infinity and p goes to 0, then this is going to simply give us e to the power minus lambda. So we are not going to prove these two, we're just going to use these results. So using these two results in equation number 1, so what we have, equation number 1, we write it like this: take the limit as n tends to infinity and p tends to 0. So we have n factorial, this remaining the same thing, rest of this same from here. So now wherever we have these n terms, we'll collect it with this limit, because this is limit for n. Okay, so we have n factorial by n minus x factorial. Okay, so we'll collect it together. Then we have p to the power x by x factorial. This I'll put it together, p to the power x by x factorial, because it only depends on p to the power x and x, right? It depends on p and x, whereas we are trying to find the limit as p tends to 0, right? So let's just keep it aside for some time, and then we'll just apply this over here. So limit as n tends to infinity, p tends to 0, 1 minus p to the power n minus x. So here this limit p tends to 1 minus p to the power n minus x, when I apply this limit over here, this is going to give us e to the power minus lambda. Okay, so we'll get e to the power minus lambda over here, and then because it becomes independent of n, so I can just drop this, taking this limit here, n tends to infinity, and as a result this is going to simply give us e to the power minus lambda, and this is going to give us n to the power x. So we have this giving us n to the power x, and then we have p to the power x. So np whole to the power x divided by x factorial, and then here we have, this is going to give us e to the power minus lambda from equation number 3. np, we define it as the parameter, np is nothing but lambda. Okay, so consequently here we're going to have lambda to the power x e to the power minus lambda by x factorial. So this, you can see, is nothing but the PF for the Poisson distribution, lambda to the power x e to the power minus lambda by x factorial. And where did we get this from? We got this result from here, which is nothing but the binomial distribution. So the binomial distribution under these limits, as n tends to infinity, p tends to 0, it turns into a Poisson distribution. Is this clear, everyone? Very simple proof. All right. Then there is a theorem, which is the theorem of sum of the Poisson distribution. So the sum of a Poisson, just like binomial distribution, the sum of two binomial variates is also a binomial variate. In a similar way, the sum of two independent Poisson variates is also a Poisson variate. And the mean of this new Poisson variate is the sum of the individual means. So if I have x and y, these are two independent Poisson variates. X is a Poisson variate with mean lambda 1, and y is a Poisson variate with mean lambda 2. Sorry, I think my mistake here. This must be Poisson. Let me correct this. Okay, so x is a Poisson variate with mean lambda 1 and y is a Poisson variate with mean lambda 2. Then suppose I have another random variable z and we define this z as simply the sum of x and y. Then z will also be a Poisson variate and the mean of z will be the sum of the individual means. Okay, in general, suppose I am having a number of such Poisson variates where each of these having different means, then the sum of all of these Poisson variates is also going to be a Poisson variate whose mean is simply the sum of the individual means. Okay, so and similar to your binomial distribution where the difference between the binomial variates is not a binomial variate, for in the case of Poisson also the difference between the two Poisson variates is also not a Poisson distribution. In fact, this difference is called as a scalum distribution. The sum of two Poisson distributions is a Poisson distribution, but the difference between two Poisson distributions is known as a scalum distribution. And that's a far complicated distribution because it involves exponentials and it involves oscillations also in the form of a modified Bessel function. Okay, so that's about the Poisson distribution. Let's take an example. Okay, let's take this scenario. Okay, a person on average receives one email message every half an hour. Okay, so there's a person who receives one email every half an hour. Now suppose you assume that emails are received randomly in time. Find the probabilities that in any particular hour 0, 1, 2, 3, 4, 5 messages are received. Okay, so that's the problem that we're trying to solve here. So how do we proceed? Okay, so here what is given is the number of emails in half an hour. Okay, what is received here? One email per half an hour. So number of emails received in half an hour is 1. So if the number of emails received in half an hour is 1, then the total number of emails in 1 hour is 2, because in first 30 minutes on an average you get one email, then in 60 minutes you'll get 1 plus 1, on an average you'll get 2 emails. So what is the rate of receiving emails? The rate of receiving emails is 2 emails per hour. Now remember here, what did we say about the Poisson distribution? It's when you have a given number of events occurring at a fixed interval of time or space. Which is the fixed interval of time? 1 hour is the fixed interval of time, and within this 1 hour how many events are occurring? There are 2 events. That is, receiving an email is the event. So in 1 hour 2 emails are being received, so lambda is going to be 2 here. So what do we define a random variable as? We define it as the number of emails received in 1 hour. Okay, so this is going to be a Poisson distribution because here the rate is fixed. The rate at which emails are received, that is fixed. It is on an average it is 2 emails per hour. So your x is a Poisson is a Poisson distribution with parameter 2. Then the PF for x is lambda to the power x e to the power minus lambda by x factorial. Lambda is 2, so it will be 2 to the power x by x factorial into e to the power minus 2. So this is the formula that we have to use here. Okay, so what is the probability of receiving 0 emails in 1 hour? So we want to find out the probability of getting 0 emails, 1 email, 2 emails, 3 emails, 4 emails and 5 emails. So probability of getting 0 emails, what will that be? All you have to do is just wherever there is x, replace that with 0. So 2 to the power 0 is 0 factorial into e to the power minus 2, which you can calculate. Probability of receiving 1 email per 1 hour is 2 to the power 1 by 1 factorial, replace x with 1. Probability of receiving 2 emails is 2 to the power 2 by 2 factorial into e to the power minus 2 and so on. Okay, I have calculated these answers using a code. So probability of receiving 0 emails in 1 hour is 0.1353. The probability of receiving 1 email in an hour is 0.2707. Probability of receiving 2 emails is 0.2707. Probability of receiving 3 emails is 0.1804, and you can see it is decreasing. Why? Because the average is 2 emails per hour. Okay, so the average will be, because the average is 2 emails per hour, so 1 email or 2 email, that is going to give us the maximum probability, and that's why we get this. Is this clear? Is this clear? Is this understood? So I'll leave this to you as a homework. Okay, so in a large batch of light bulbs, the probability that a bulb is defective is 0.5%. For a sample of 200 bulbs taken at random, find the approximate probabilities that 0, 1 or 2 bulbs are respectively defective. Okay, so please do this. All right, any questions do you have before I move on to continuous distributions? Any questions? So if there are no questions, then we'll proceed with continuous distributions. This would be the last topic in this module. That is continuous distribution. We are going to talk about only one distribution, which is known as the Gaussian distribution. Really important distribution, which is used again almost everywhere, as you will see. Some of the examples that we will do, a couple of examples. So coming to continuous distributions, we are going to talk only about the Gaussian distribution. So what is a Gaussian distribution? It's a very important distribution. It is used in statistics, okay, in natural, wherever there are natural processes involved, okay, and even in social sciences also, okay. In humanities, if you have some friends from humanities, they will also probably be making studies of random natural processes which follow a Gaussian distribution. And why is this important? It is important because of what is called as the central limit theorem. So what the central limit theorem it says is, this is the statement, essentially the central limit theorem it says is, for any kind of distribution, be it binomial distribution or Poisson distribution or any other distribution, or log normal distribution or Gauss normal distribution, any distribution, if the number of samples becomes tends towards infinity, the total number of samples, it tends towards infinity with no other restriction, then that distribution is going to become, ultimately it's going to become approximately a Gaussian distribution. Okay, so ultimately every distribution becomes a Gaussian distribution if the number of samples increases. Okay, so let's say the plot that you have, the COVID during COVID-19, the number of cases that you get, that's a natural process. That is going to, because this has gone on for like over 2 years. So now the data that we have, okay, we have a tremendous amount of data. The number of samples is really large. So as a result, we are going to have a normal distribution in such a case. Did somebody text something? No. Okay.
Sir, Deva sir is waiting for his class.
Debo, just a minute. Debo, 5 or 10 minutes? Yeah, it's okay. He said he will take after like 10 minutes after I finish this. Don't worry. Okay, so this is what the central limit theorem says. That means every distribution becomes a Gaussian distribution. Okay. So now the physical process quantities, okay, these are because whenever you make measurements of any physical quantities such as errors and so on, so those errors will have distributions which are nearly normal. So that's why understanding Gaussian distribution is really important, especially because next year when you in your final year, when you're going to do your projects, so in your projects you will be dealing with errors. So there you will see, you will have to model your errors in terms of normal distributions. Okay. So now we can also define a random variable which has got a Gaussian distribution. So it is defined like this. So suppose I have a random variable x and it has got some parameters. One parameter is mu and another parameter is sigma squared. By now you already know what is mu and sigma squared because we have already discussed this in the previous class. Mu is the mean and sigma squared is the variance. Okay. But let's just say that we have some parameters mu and sigma squared. Then the Gaussian or the normal distribution, it has got the PDF which is given in this way. Okay, the value of the probability at x for these two parameters mu and sigma square is 1 by sigma to the power 1 by sigma into root over twice pi e to the power minus half x minus mu by sigma whole square. So if I have a random variable which follows a Gaussian distribution, then we say that x, it is similar to n mu sigma square. So just like this, as we had written over here, this is for a binomial, we write it like this. Poisson, we write it this way. And for a Gaussian or a normal distribution, we say x, the random variable, it is similar to, instead of bin or po, we'll just write n, and the parameters are mu and sigma squared. Okay, so these are the parameters. Okay. So now what is the mean and the variance of a Gaussian variant? Very simple. The mean is mu and the variance is sigma squared. Now we can actually prove this, which again we'll prove it in your research methodology paper. Okay. So I'll show you how a Gaussian distribution this it looks like. There's a plot. Let me generate the plot. Yeah, so this is a Gaussian distribution. This is for mu equal to 1. You can see here, when I put mu equal to 1, the center, all three, the red, green and blue, all of them are Gaussian distribution. Mu is equal to 1. For all of these distributions, mu is equal to 1. So this is 0, this is 2, then this is mu, this is 1. Mu is equal to 1. That means the center of the distribution. Okay, so for each of these distributions, you can see that the center is at mu equal to 1. But what is the difference between these? The difference is in the value of sigma. So for the red one, for this red plot, sigma is 1. For the green, sigma is 2. For the blue plot, the sigma is 3. And you can see here, as sigma increases 1, 2, 3, the distribution becomes wider and wider. As the distribution becomes wider and wider, the height of the distribution decreases, which has to happen, right? Why should the height decrease? With increasing variance, the height, why should it decrease? I mentioned some time back. Why should the height also decrease? Does anybody remember? We saw the same thing in the binomial distribution, right? As the distribution became wider, the height of the distribution became smaller. Why is that so? Because the total area has to be 1. So here also, the total area under the Gaussian distribution, the total area has to be equal to 1, and that's why this is decreasing. Is this clear, everyone? So if I keep the mean to be constant and change the sigma value, this is what you will get. But on the other hand, if I keep the sigma to be constant, you can see sigma is constant. You can see all of them, they have got the same length. For instance, the red one, you can see the length, this length. The green also same width, and the blue also same width. All of them are equally wide. But what is the difference between the three? The difference between the three is the position of the center. For the red one, the center is mu equal to 1. Okay, so it is centered at this point. For the green one, the mu is equal to 2. So the center of the green is here. And for the blue one, the mu is equal to 3. The center is over here. So what we have to do is, we have how do you produce these variations in the Gaussian PDF? You have to just remember this. If you change mu, you are shifting the curve along the x-axis. Changing mu, here you are changing mu. You are going to shift the curve to the right or the left. Okay, increasing mu will shift the curve towards the right side, decreasing mu will shift it towards the left side. And changing sigma, it is going to make the graph broader, or it's going to make it narrower. Okay, so that's how you can control the shape of the Gaussian. Okay, now what happens at x equals to mu plus or minus sigma? So we have the mean and then plus sigma or minus sigma, these two sides. What happens? The value of f, it becomes 1 by root e times, that is around 61% of its peak value. You can see this here in this plot much clearer. Okay, so this is the Gaussian distribution. Okay, so this is the mean, this is the mu, this point is mu plus sigma, and this point is mu minus sigma. At both mu plus and mu minus sigma, you can see the value is 0.61. okay, here the maximum value is f max, and at mu plus sigma and mu minus sigma, the value becomes 0.61 times f max. That means it becomes 61% of its peak value. Okay, so remember this number. Okay, 61%. Okay, that's going to be very helpful for your problems, let's say in statistical physics and so on. So now we come to a very useful tool, which is called as the standard Gaussian distribution. Again, you will find it very helpful when you do your course in statistical physics in your 4th semester. So what is standard Gaussian distribution? It says that I can produce a standard Gaussian distribution if I make a transformation. So if I want to go from one normal variate to another random variable z. So x is a normal variate or a Gaussian variate, and z is another random variable. Then we make a transformation from x to z, and the transformation is, one moment, and the transformation is z is defined as x minus mu by sigma. Okay, then this z is known as the standard variable. Okay, and its PDF is known as the standard normal distribution. This is not this phi, this is small phi. Okay, so this is known as a standard variable, and the probability density function of this z is known as the standard normal distribution. Okay, and it turns out this is also Gaussian. So what is the PDF of a standard Gaussian distribution? How does it look like? So the new random variable, okay, which is given in this way. The PDF is given in this way. The PDF of the standard Gaussian distribution is 1 by root over twice by e to the power minus z square by 2. And as you can see here, if you compare it with this, let's see here, let me write it down. So for a Gaussian distribution, it is 1 by sigma root over twice by e to the power minus half x minus mu by sigma squared. Okay, so this is the distribution, and here look at the standard distribution compared to 2. This is f of x, the PDF for a Gaussian. You look at the PDF for a standard Gaussian. Comparing these two, what do you see? If you compare this with this, what do you see? First of all, here 1 by, there is supposed to be a sigma here, but there is no sigma. What does that mean? It means that sigma is equal to 1. Correct? Is that clear? And that is also confirmed over here. Okay, sigma is equal to 1. And what about the mean mu? What about the mu? Because you can see here, if I put mu equals 0, you can see here, if I put mu equal to 0, sigma equal to 1. So what do you get here? We get minus x square by 2 or minus z square by 2. So this also implies that mu is equal to 0. Is that clear? If you just compare these two. Okay. So you have 1 by, here is supposed to be a sigma here, and there is supposed to be a sigma here, that e to the power whatever it is, sigma here. There is nothing, there is no sigma, that means the sigma must be equal to 1. And there is, you are not x minus mu, you are not subtracting anything from z, that means you are subtracting 0, that means mu is equal to 0. So if you compare this, then the random variable z has got a mean of mu and the variance sigma is equal to 1, it means sigma square is also equal to 1, so variance is 1. So in other words, if I make this kind of a transformation, the transformation z equal to x minus mu by sigma, it takes us from a Gaussian variate to another Gaussian variate. So this first Gaussian variate, it was having a mean mu and a variance of sigma squared. From here we went to another Gaussian variate. This Gaussian variate had got a mean of 0 and a variance of 1. Okay, so because this of this form, the standard Gaussian, it becomes very convenient for us. Okay, is this clear? Because of the specific form, because for a standard Gaussian you don't have to remember its mean or the variance. Very easy, the mean is 0 and the variance is 1. So because the mean is 0 and variance is 1, it becomes very easy for us to work with this. Okay, so I'll plot this over here. Okay, so this is the plot for a Gaussian distribution. Okay, it's not so clear over here. So this is for f of x. Okay, and the mean is mu and the variance is sigma squared. From here, by making this transformation, okay, what is the transformation? Z is equal to x minus mu by sigma. Whatever is the x here, x minus mu by sigma. By making this transformation, I get this distribution, which is phi. And what is this phi? Phi is it is not a function of x, it's a function of z. And what are the parameters? The mean is 0 and the variance is 1. Is that clear? Okay, so this is the kind of motion that you are doing. This is the kind of transformation that we are making from one kind of a distribution to another kind of a distribution. Now you will see the use of this standard Gaussian distribution by looking at the CDF, the cumulative density function. Okay, the CDF of a Gaussian distribution is this. Now you remember what is CDF? You have to integrate, right? Now look at this expression. Integration of this is really challenging. Integration of e to the power a square, it's very challenging. So it is very difficult for you to evaluate this integral analytically. So in that case, we use the standard Gaussian, because the values of the integral for the CDF, for the standard Gaussian, it is available in the form of a table. Okay, so if I take the CDF of a standard Gaussian distribution, this is what it is. The standard Gaussian distribution, we use capital phi. This is capital phi. Okay, and here the PDF we are using small phi. Note the difference. Okay, this is small letter phi and this is capital letter phi. So small letter phi for the PDF of the standard Gaussian, and capital letter phi is for the CDF of the standard Gaussian distribution. So we have to basically integrate this. So if you integrate the standard, this is the standard Gaussian PDF, its CDF is going to look something like this. Okay, so what does this really mean? What it means is this. So suppose I want to find out what is the value of the CDF at phi at A. Okay, so let's say I take this point A. At this point A, I find out what is the value of the CDF. This is the value that I get. So what does this value correspond to? It corresponds to the area under this shaded part. The total area under this is equal to the value, this value. Okay, is this clear, everyone? After all, this is what is a CDF, this is what it stands for. So I'll show you the table of such a standard Gaussian distribution. This is a table, and I'll do an example to for you to understand how to use this table. Let's use some results here. The result is, if I want to find the CDF at some negative value, that is equal to 1 minus the CDF at the corresponding positive value. So which means, so let's say I want to find out what is phi of minus 0.56. This is equal to 1 minus the value of phi at 0.56 itself. Okay, just as an example. Okay, so we can find out the probability, we can find out the value of the CDF at negative values also. So you can understand it very easily from here because of the symmetry of this problem. So I want to find out what is the value of the CDF at minus A. At minus A, it gives us this value. Okay, and at plus A, it gives us this value. So this is the value at phi. This is phi at minus A. This is phi at plus A. This is 1. Maximum value is 1. So if I take the difference between these two, this will be the difference. This difference, and you can see here, it will be same as this. Okay, so that's how we are able to write this expression. Then for constant values, some results. For constant values A and B, for the probability that Z is less than A is phi at A. The probability that Z is greater than A will be 1 minus phi at A. The probability that Z lies between A and B is phi at B minus phi at A. Okay, so knowing this phi, we can find out the CDF of another distribution in this way. So the CDF, so this is the CDF for the standard Gaussian distribution. Let's say I have another Gaussian distribution and that one has got a CDF F. So we can find out what is that F. All I need to do is this phi, because what is X? X is because that will be equal to, because I'm trying to find out the probability that X is less than X. So that corresponds to whatever is the value of Z that we are trying to find here. And what is the Z here? Z is equal to X minus mu by sigma because of this transformation, because we have already defined Z in this way. Z is X minus mu by sigma. Okay, so whatever value of X you have given me, so that X minus mu by sigma, that will give me the Z. So put it here, so we get the value at the CDF. That will be nothing but the probability that, you know, the value of X is less than this small x. Okay, so and this we can get it from the CDF of the another function. So you can actually find out this using this. Okay, I'll do some examples, then it will become clear. This result, I'll not go into this. Let's straight away jump to the example. Let's take the first example. The first example is, if a random variable is such that, suppose I have a random variable which is normally distributed, we need to find out the probability that X lies within 1 sigma, 2 sigma and 3 sigma of the mean. Okay, let me take this to a new slide. So this is the problem that we'd like to solve. Okay, we want to find the probability that X lies between 1 sigma, 2 sigma and 3 sigma of the mean. What does this mean really? It means this. So suppose I have a distribution. Let's take, this is a normal distribution. Mean of mu and let's say variance of sigma squared. So let's say this is how the distribution looks like. Okay, so let's say this is the distribution that this is our distribution. This is the normal distribution that we have, and here the mean is here. This is the mean, which is, this is the mean mu, and here we have mu plus sigma, then we have mu plus 2 sigma, and then here we have mu plus 3 sigma. Okay, then on this side we'll have mu minus sigma, here we'll have mu minus twice sigma, and here we'll have mu minus thrice sigma. So what do you mean by this? The probability that x lies within 1 sigma, probability that it lies between 1 sigma is this one. Between the value of x, it lies within this range. This is what I want to find out. The area, this is what I want to find out. The probability that it lies within 1 sigma. This is what we'd like to find out. Similarly, if I want 2 sigma, that means what is this larger area? 3 sigma means what is this larger area? This is what we are trying to find out over here. Okay, so let's quickly solve this problem. So here, let us say I define A is equal to mu minus n sigma. N is some integer value. You just have to put the value of n equal to 1, 2 and 3 to get the answer. And B equals mu plus n sigma, where n equals 1, 2 or 3. Okay, so that's what we'd like to do. So I want to find out what is the probability that the random variable, it lies between mu minus n sigma and mu plus n sigma. This is what we'd like to find out here. Okay, calculate the probability that x lies within this. This is what we'd like to do. Okay, so how do we go ahead and how do we proceed with this? So we're going to use this result. Okay, the probability, you can see here, we're going to use this result. The probability that this lies within this is given by this. Let me grab this result. This is the result that we're going to use. The probability that this x lies within a given range. Okay, it is given as this. So this is equal to probability from x, I'm going to z, goes from minus n to plus n. How did that happen? Because we have z was defined as x minus mu by sigma. This is what z was, right? So from here we get so we have x minus mu is equal to sigma into z, which gives us x equals mu. Okay, just a second. Let me do it in a different way. How we got it is this way. When x equals mu minus n sigma, what will be the value of z? We know that z is equal to x minus mu by sigma. This is z. So this will be, we substitute the value of x here. X is mu minus n sigma minus mu divided by sigma, and this is going to give us minus n. Similarly, okay, I'll leave it to you. When x is equal to mu plus n sigma, then z will be equal to plus n. So that's why you wrote it like this. X lies between this, then z will be minus n here, and x, when it is mu plus n sigma, z will be plus n. So that's how you got this probability. Okay, everyone, is this clear? Okay, so now I want to find this. So for that, I'm going to use another result here. The result is this. If I want to find out the probability that z lies between a and b, I'm going to use this result. It is just simply the because we already know this is true for CDF, right? It's just phi b minus phi a. Probability that lies between a and b is phi b minus phi a. So this is equal to the phi at a and b. So we have this is a and this is b. Okay, so we have b, phi b is n minus phi minus n. Okay, this is what we have. Now this is easy because we already know that whenever you have this result, if I want to find out the negative values, okay, the negative values, all you need to do is you do 1 minus the corresponding positive value. So this gives us, so we have phi n minus, then we have, this is nothing but 1 minus again phi n. Okay, and this minus and minus will become plus, and as a result we will get twice phi n minus 1. Okay, so now it's really straightforward. So if I want to find out, so therefore if I want to find out the probability that your x, it lies within 1 sigma. X lies within 1 sigma means x lies between mu minus sigma and mu plus sigma. So mu minus sigma less than x less than equals mu plus sigma. That means, what does this mean? It means n equal to 1. Okay, as can be seen over here in this formula. So this is simply equal to, as you can just take this from here, it is 2 into phi. What is the value of n? The value of n is 1. So phi 1 minus 1. Now phi 1, what is the value of phi 1? This is where your table will come into picture. Okay, this table which I have shown here, this is where it will come into picture. So I want to find out phi 1. So phi 1 means this one. I want to find out phi 1. So you can see here z, these are the z values. Okay, these are the z values and these are the decimal points. Okay, so we just look for 1 here. So we have 1, right? 1.0 is here, and then on the decimal side we have 0, 0. Okay, so what does this mean? It means this and this together, if I just add these two, okay, if I add this with this, I'll get 1.0 plus 0.00, so 1.00. So what we are getting here is, this will be the value. Okay, so phi of 1.00, it is equal to 0.8413. This is the value. Okay, so we'll just take this here, 0.8413, and we'll substitute over here. So this is equal to 2 into 0.8413 minus 1, and if you calculate this, it will come to 0.6826, which is basically 68.3%. Okay, so there is a 68.3% probability that x lies between 1 sigma. X lies within 1 sigma. Make sense? Does this make sense, everybody? What about this one? The probability that it lies within 2 sigma. Mu minus 2 sigma less than x less than equal to mu plus 2 sigma. What will be the answer? We'll just pick up the answer from here. It will be 2 into phi. In this case, what is n? N is equal to 2, right? N is equal to 2. So phi of 2 minus 1, which is equal to 2 into, we need to find out what is the phi of 2. So what is phi of 2? Again, go back here. Phi of 2. So 2 is here. So 2 is here and 2.00. So it means this is the value that we're looking for. So phi of 2.00 is 0.9772. So this value is already given here. We'll just substitute over here. So 0.9772 minus 1, which gives us 0.9544 or 95.4% probability, which makes sense because 1 sigma the area is smaller, 2 sigma the area has now become larger, right? 2 sigma means this area, 95% of the area. Is this clear? Is this clear, everyone? The third one I'll leave it to you, okay? The probability that it lies within 3 sigma minus 3 sigma less than x less than equal to mu plus 3 sigma. I'll leave it to you. This is for n equals 3. Understood, everyone? Any questions? Any questions? Anybody? Okay, great. Let's look at the next problem, which is the last problem, and I'll stop here. The next problem is this. Okay, let me grab this problem from here. Okay, the problem is the time taken for a computer packet to travel from Cambridge, UK to Cambridge, Massachusetts, MA for Massachusetts, is normally distributed. So essentially what it means is this. So we have, let's say, the United States, okay, this United States here, and across the Atlantic we have United Kingdom, okay, this somewhere on the tip of Europe. So we have the United Kingdom here. So there is a place here, okay, that place is this Cambridge. This is Cambridge, which is in the UK. Okay, and I don't know where Massachusetts is, somewhere in the United States. There's another place called as Cambridge in the US, in a state called Massachusetts. So these are two different places, same name, but the two places are separated by the Atlantic Ocean. Okay, so a computer packet which travels through the internet. Okay, so how does America and how do America and England, how do the UK, how do they connect to each other? Via the undersea cable. So under the ocean there is a fiber optic cable, okay, fiber optic ring cable. So America is connected to that ring and UK is also connected to this ring. So let's say you take a computer packet, a packet of data, and you send that data across this cable and it reaches Cambridge. Okay, so how much time does it take for this computer packet to reach here? So this is the data which is given. So the time that it takes has got a normal distance. So let's say the time taken is t. This time is a normal distribution. Okay, it's a Gaussian distribution with certain mean and certain variance. This is what you need to find out. What is the mean and what is the standard deviation of this distribution? This is what you need to find out. Okay, so to find out the mean and the standard deviation, some data is given to you. What is the data? It says that 6.8% of the packets they take over 200 milliseconds. Okay, around 6.8% of the packets take over 200 milliseconds to make the journey, and 3% take less than 140 milliseconds. Now, how do I understand this? You can understand this in the form of a graph. Like I said, what is the random variable? The random variable is the time taken. Okay, that is the random variable. So it is some Gaussian. Okay, it is some Gaussian, but we don't know what is the mean and what is the standard deviation, that we don't know. So it is some Gaussian. This is what we want to find out: the mean and the variance and the standard deviation of this Gaussian distribution. This is what we are trying to find out. So let's say this is the Gaussian distribution. Okay, this is a Gaussian distribution. What it says here is this: over 200 milliseconds and under 140 milliseconds. Okay, over 200. So let's say we have more than 200 milliseconds. Let's say this is 200 milliseconds. This is time in milliseconds, and this is 140 milliseconds. What it says is over more than 200 milliseconds, more than time taken for more than 200 milliseconds. When the time taken is more than 200 milliseconds, this area, it corresponds to the probability, it corresponds to 6.8%. And the time taken, which is less than Okay, I think I should do it to be more realistic. 140 will be somewhere here. 140 is over here. Okay, less than 140 milliseconds. Okay, that means this area is just 3%. Okay, now the question which they have asked is, based on this information, using this information, we need to find out what is the mean of this distribution and what is the standard deviation, that is the spread of this distribution. This is what we need to find out. Have you understood the problem? Have you all understood the problem? Is this clear? Yes? No? Anyone? Okay, if it's not clear, I suggest that you go through this again. Okay, let me proceed to solve this problem. So let's take this. Okay, so given, what is given? The probability that the time taken is more than 200 milliseconds. What is this probability equal to? It is 6.8%. Okay, which is of course 0.068. Okay, 6.8% is 0.068. Okay, so this is what is given to us. Okay, now this will be equal to, okay, I'm going to use this result, that is this result. If I'm using greater than symbol means we have to use 1 minus phi a. Okay, greater than symbol means always 1 minus phi a. So I'm going to use that same idea. So this implies, because there is a greater than symbol, this means we have to use 1 minus phi of what? Phi of what? So here a is 200, right? So what is the change in the value, the transformation? Z is equal to, instead of x I'm going to use t, so t minus mu by sigma, right? So what is t here? T is 200 minus mu divided by sigma. Okay, so this is what it is. So this is equal to 0.068. Okay, so from here it is easy. All I have to do is just find out what is this quantity. So this will be equal to 1 minus 0.068, which is 0.932. Is this clear? Now that means this quantity is equal to 0.932. Okay, now can I write this 0.932 as phi of something? Okay, can I write this as 0.932 as phi of something? Yes, we can. How we can do that is, again, we go to the CDF table. So here in the CDF table, we look for 0.932, which is easy to find because 0.932 is somewhere here. You see here 0.9306. Let me just grab this part from here. Okay, so we are looking for 0.932, which is 0.932, and 0.932 is over here. Okay, so for what value of z do you get 0.932? For what value of z do we get 0.932? So you just move this way, 0.932, you get this, and move upwards, you get this. Then add these two numbers. So which means phi of, what is here? We have 1.4 and here we have 0.09. So 1.4 plus 0.09 is 1.49. Okay, 1.4 is equal to 1.4 plus 0.09. So which means phi of this is equal to this. This implies that whatever is the argument in both the cases must be the same. It means this should be equal to 1.49. Let's call this equation number 1. Is this clear, everyone? Is this understood? Make sense how I got this? Can I proceed? Okay. Another thing which is given is for time t less than 140 milliseconds. This is given as 3%, right? 3% means 0.03. Okay, so when it is less than, then what formula do we use? If it is less than, we simply use phi of a. Okay, so this will be equal to simply phi of a. What is a? 140 minus mu divided by, remember phi, the argument is z, this is the random variable t, we have to make this transformation, divided by sigma. Okay, this is equal to 0.03. Now what will this value be? For that again we have to go here, 0.03. Where is it? One moment. Can't find out 0.03 from here. Okay, because it does not, the smallest is 0.5. So instead of that, what we'll do is we'll do a trick here. What we'll do is we'll subtract from 1. So 1 minus both sides. We'll subtract from 1. So 1 minus this is equal to 1 minus 0.03. Okay, we'll subtract from here. Now we are going to get some result. So from here we get 1 minus this quantity is equal to 0.970. Okay, so now what is this going to be equal to? This is going to be equal to, because we already know that, where is this? We use this result. 1 minus phi a is equal to phi of minus a. 1 minus phi a is phi of minus a. So 1 minus phi of a is phi of minus a. So this is equal to phi of the negative of this quantity, which will simply become mu minus 140 divided by sigma. Okay, so this is going to be equal to 0.970. Now let's find out 0.970. Not here. 970 is, yeah, somewhere here. Okay, so we are looking for 970 somewhere over here. So which means we are looking for this one, 1.8. okay, and that is, I think, is 1.89, I think, yeah, 1.8, because on top that was 0.09. yeah, so this will be nothing but phi of 1.89. so this implies mu minus 140 divided by sigma is equal to 1.89. Call this equation number 2. So all you need to do is just solve equation 1 and 2. These are two equations, equation 1, equation 2. So simultaneously solving equations 1 and 2 gives, solving equations 1 and 2, it gives us the value of mu, and I got the value of mu to be 173.5 milliseconds, and the value of sigma, I got it to be 17.8 milliseconds. So therefore the time, the time taken for the packet to travel is a Gaussian distribution whose with mean 173.5 milliseconds and the variance 117.8. okay, we don't write milliseconds here, just the number is enough. 173.5 and 17.8 squared. So essentially what it means is this value that we're looking for, 173.5 milliseconds, this is the value. Okay, so most of the packets will take around 173.5 milliseconds. So this question could be asked in a different way. Find out the mean time taken for the computer packets to travel from between these two locations. So that will be, mean time will be 173.5. okay, so with this I come to the end of this module on probability. If you have any questions, you may let me know, otherwise we can stop here. In the next class, I wanted to finish this today itself because tomorrow I would like to take a class. I would like to start another module which is called as special functions. Okay, so if you have any questions, you may ask me, otherwise we can stop here.